Good morning, students. Today, we're going to talk about nitrogen narcosis and decompression sickness. This is the second lecture and the very last in your series of topics on respiratory physiology. Okay. During this lecture, you're expected to know what barometric pressure is. If you would recall from the previous lecture, I explained what barometric pressure is. And this time around, you will be expected to explain how barometric pressure affects nitrogen concentration. You should be able to understand the effects of breathing high concentrations of nitrogen. And you should be able to discuss the cause of decompression sickness. You should be able to differentiate between nitrogen narcosis and decompression syndrome. Okay, so this is a general outline that I have given this lecture. We're going to be going with this outline. Okay, so we all know, if we can recall, that air is made up of not just oxygen, made up of gases, nitrogen, argon, carbon dioxide, and so many other gases. And the highest concentration of oxygen in air is 20.95% or thereabouts. We have about 78% of or 79% nitrogen in air. Now, our human body is naturally adapted to breathe oxygen or breathe air from the atmosphere. Remember, we said atmospheric air is the same as the air you breathe from the atmosphere. And the human body is naturally adapted to breathe that air at a pressure of 160 torr at sea level. Torr simply means millimeters of mercury. So remember that your hemoglobin has to combine with molecules of oxygen, okay? So the molecule that carries oxygen is hemoglobin, and it has to be saturated at approximately 98%. So when you have higher pressures of oxygen, they cause just little effects in an increase in oxyhemoglobin. Remember, oxyhemoglobin is when the hemoglobin combines with oxygen, okay? But where you still have some large amounts of oxygen, which is unburnt, which will pass into the solution, into the blood plasma as the pressure increases, okay? When you have longer term exposures to high oxygen, then you have a situation which is called oxygen toxicity. So your body should not be exposed to excessive oxygen. Let's go on. Now, before we continue, let's quickly look at 4 most common methods of reporting gas pressures. We're talking about gas. Everything is about gases. When we say nitrogen narcosis is about gas. When we say decompression sickness is about gas. But this time around, we are focusing on one particular type of gas. Now, millimeters of mercury, this is the most common type of method of reporting a gas pressure. And that's approximately 760 millimeters of mercury. You have 760 millimeters of mercury is the normal atmospheric pressure. And torr is just this unit of measurement. It's not an SI unit, unlike millimeters of mercury that's commonly used, but the most commonly used torr is unit of measurement for respiratory therapists. Most of the time it's used in Europe. It's also equivalent to 1 torr is equal to 1 millimeter of mercury, okay? So we have centimeters of water, you must have heard that too. And we also have pounds per square inch. Now, let's look at the effects of increased barometric pressure. We're just looking at the preamble. So by the time we start talking about the real meat of the matter, you would understand what we're talking about. Now, remember your Dalton's law of partial pressures. And the partial pressure of a gas is a mixture of each gas in a mixture. It is the pressure that the gas will exert if it were by itself in a container. Never forget that. So that's why you have partial pressure of oxygen, you have partial pressure of nitrogen, you have partial pressure of carbon dioxide, okay? Now, this is quite different from Henry's law. Now, all these laws are put into effect when we're talking about gases and gas exchange in the body, okay? That's basically what goes on in the respiratory system. So Henry's law is the solubility of a gas in a liquid. which is directly proportional to the gas that is over the liquid. Let me come again. The solubility of a gas in a liquid is proportional to the partial pressure of the gas which sits over the liquid. For example, an example is when you have a bottle of Coke. It's in a pressurized container, it's covered, there's some carbon dioxide over the bottle of Coke or Pepsi, okay? So, and there's also some carbon dioxide dissolved in the liquid in the bottle, okay? So by the time you open up a bottle of Coke, maybe you have shaken it very well, and just sometimes you discover that you open it up and it spills over and you hear that hissing sound. That's because as the CO2, the carbon dioxide on top of the gas is being released, the pressure is falling. So is the pressure in the liquid in the bottle as well. So it's a direct proportion, and it's also followed with a constant. The solubility of a gas in a liquid is proportional to the partial pressure of that gas over the liquid. So that's Henry's law, and we're going to be looking at that a lot. So now just let's quickly take a look at this. Standard atmospheric pressure at sea level is 760 millimeters of mercury. Now let's look at the different gas components. Remember, we have talked about partial pressure. Let's look at carbon dioxide. You can see that the percentage of air, carbon dioxide in air, 0.03%. So you have 0.03% of carbon dioxide in air at a partial pressure of 0.2 millimeters of mercury. You can see the partial pressure of oxygen, 159.1 or 160. That's where we got the 160 total of oxygen, okay? Of nitrogen, we have 79% of nitrogen makes up air, and the partial pressure is 600.7 thereabout millimeters of mercury. And you can see that of water vapor, okay? Still going on, you remember the last lecture we talked about sea level and high altitude. Sea level just means where you are, okay? You don't need to go to the beach before you say, okay, is that sea level? Sea level is where you are, okay? High altitude is up in the mountainous mountains, in the sky, upon mountains at different feet, which we explained in the last lecture. Okay, so at sea level, the barometric pressure is 760 millimeters of mercury, which is called 1 atmosphere. Okay, so at the depth of 33 feet, that's about 10 meters, pressure increases by 1 atmosphere. So when you're at the depth of 33 feet, that pressure there is 2 atmospheres. So this is because you have air above water, and it is due to the weight of that water itself, okay? Now you can see the effects of barometric pressure here. Remember barometric pressure, okay? There's something called the Lorenz-Smith effect. Now, humans cannot breathe more than we were designed to breathe, okay? I'll take that again. You cannot breathe more than you were designed to breathe. And if you attempt to breathe in extra, you are looking for trouble. So when you are on the Earth's surface, I'm not talking about space now, you can continuously breathe 100% oxygen, but that's just for between 24 and 36 hours. After that, your lungs start getting toxic. We call it pulmonary oxygen toxicity. It starts at that time. So now you can see all these symptoms here of lung toxicity. That's because you've been breathing 100% oxygen. So we were not designed to breathe 100% oxygen for more than 36 hours. So what happens is the person starts experiencing chest pain. We say substernal chest pain. Some people might even think it's ulcer, okay? In this country, everything is ulcer, but not everything is ulcer, okay? Person could start having dry, non-productive cough. Person could start having reduction in vital capacity. Remember what your vital capacity is. Then the surfactant, you remember your surfactant production in the lungs, in the alveoli, you don't have it anymore. And that's really dangerous. You remember what patchy atelectasis is. You can see that on chest x-ray. And then if you are continually exposed to 100% oxygen, you could have microhemorrhages, okay? And then lastly, what is called permanent lung fibrosis, okay? through all the stages of oxygen toxicity, it can be reversed. But once it gets to fibrosis, it's an irreversible process. The scarring process is irreversible. It can never be reversed. So you can see the effect of breathing in 100% oxygen for more than 36 hours. Now, there's another effect called the Paul Bert effect. Notice that all these names were developed by scientists who researched into how the body works, okay? So the Paul Bert effects at a pressure greater than 2 atmospheres, seizures can actually occur, okay? In layman's terms, we say convulsions, okay? That is because you have too much oxygen in the brain, cerebral oxygen toxicity. So this neurotoxicity was first described by Paul Bert as far back as 1878. Now, for example, in deep sea, in the deepest parts of the sea, so not deepest, deep sea, or in mines, in all these places you don't have oxygen there, okay? So the problem here, you have high barometric pressure. So the increased pressure creates two major problems, okay? You have this compression effect on the body and the internal organs, and you have a decrease in the volume of gases. That's what happens. Now, let's now go to nitrogen narcosis proper. What exactly is nitrogen narcosis, okay? Nitrogen narcosis is also called rapture of the deep. It's an altered state of mind, which is caused by breathing nitrogen at a very high partial pressure. We'll get to see what happens and why that occurs shortly. Now, the deeper a diver descends, well, a diver, most of you know who a diver is. A diver is someone who moves into the deep waters for any purpose. Some may be for recreation, some may be marine scientists, some may actually be armed forces personnel, some may just do it for fun, but a diver is always a diver and is exposed to everything that happens underwater. So once a diver descends, the higher the partial pressure of nitrogen and other gases in the air will be. So the deeper a diver descends, the higher the partial pressure of nitrogen and other gases in that air that he's breathing will be. So the deeper a diver goes, the greater the narcosis. When we say narcosis, if we remember, it's from the word narcotic. Now, narcotic is, we say, those class of drugs which we classify as dangerous drugs, which make you fall into a state of coma. Okay, narcotic drugs, there are a whole list of them. I would advise that if you are in the habit of, taking narcotic drugs, you should stop, because you're actually destroying your brain and you are setting yourself up for a myocardial infarction, which is a heart attack. Okay, so let's continue. Narcosis refers to unconsciousness or stupor caused by some types of medication. Stupor refers to lethargy. You're just tired, you can't just do anything. Suppression of sensations and feelings, okay? So nitrogen narcosis means the narcotic effect that's produced by nitrogen at that high pressure, okay? Remember, we're talking about nitrogen now. Nitrogen is the gas at stake now. So it's common, this narcosis is common in deep sea divers. They breathe compressed air, which is air under high pressure. Remember, we said the composition of nitrogen in air is what? In air is what? Is about 79%. Okay. Now, 80% of atmospheric air is nitrogen. Yes, 79, 80%. It is an inert gas. It doesn't produce any known effects on the functions of the body when you are at sea level. You won't notice anything when you're at sea level because it's inert. It doesn't do anything. But once you start going deep down, that's where the problem lies. Now, the narcotic effect of nitrogen will appear as a result of breathing pressurized air. We've said that before in deep sea. An altered mental state, similar to someone who is drunk. If you've ever seen a real drunkard before, who is drunk, who doesn't know where he is, that's what happens. The mental state is altered. Now, nitrogen is soluble in fats, and in deep sea, that nitrogen escapes from blood vessels and gets dissolved in fats. And you have fat in various parts of the body. You have fats around your neural membranes, around your myelin sheaths. Fat is everywhere in the body, okay? And you have different types of fat. You have brown fat, you have white fat, but you have different areas where you have fat in the body. So nitrogen will escape from blood vessels and goes and gets lodged into the fat. Okay, so dissolved nitrogen normally acts like an anesthetic agent. It will suppress the excitability of the neurons. Okay, it goes there to say, okay, I'm here. You guys are not going to work again. So it suppresses the excitability of the neurons. So that nitrogen remains in dissolved form in the fat until that person, gets out of that deep sea. If the person remains in deep sea, the nitrogen remains there in that dissolved form. So the first symptom that person begins to notice, first of all, it depends on the depth. Okay, so at a depth of 120 feet, the person becomes, first of all, jovial, very, very, very jovial, extra jovial, not normal jovial, careless, lack of insight, So between 150 to 200 feet, you start noticing, oh, this person is getting drowsy, or he's getting drowsy. Between 200 to 250 feet, you start getting tired, very tired and weak, okay? Extreme fatigue and weakness. You can't make a proper judgment anymore. You can't concentrate even while underwater. So he's not able to perform any skilled movements. And to be able to swim underwater, you need some skilled movements, okay? He can't do that anymore. That's why most of them drown before they get help, okay? But if they're able to show that there's something going on, they could get help. So at depths of greater than 250 feet, the diver becomes totally unconscious, okay? We have said he may have trouble coordinating, okay? He can't do precise movements anymore. Thermoregulations, that shivering reaction that helps to keep a diver's body warm is reduced because of nitrogen narcosis. Okay, he can't reason, he can't recall information. Okay, it's that bad. So now the only thing that can reverse all these symptoms is for the diver to return to a depth of about 60 feet. And he goes slowly, doesn't go fast, he goes slowly. Okay, so let's go to decompression sickness. It's still about nitrogen, okay? Now, people confuse nitrogen narcosis with decompression sickness. It's not the same thing, but it's still caused by nitrogen. Now, decompression sickness is a physical condition where it's caused also by the formation of nitrogen bubbles, okay? So although these bubbles are very, very tiny, they can actually block blood flow in the vessels in various parts of the body and cause irreversible damage, okay? Now, the condition occurs when the diver attempts to quickly swim fast back to where atmospheric pressure is, okay? Maybe he found out that he wasn't feeling okay, and instead of, relaxing and going slowly, he decides to swim very fast. Okay, so nitrogen bubbles start to block the flow. Now, this decompression sickness, also known as dysbarism, compressed air sickness, casein disease, the bends, or diver's palsy. So you can see all the different names given for decompression sickness. Now, the symptoms could be very much the same, they're similar. Okay, you have severe pain in the tissues, especially the joints. That numbness is there, tingling or pricking. It's called paresthesia, itching, paralysis, muscle cramps, coronary arteries. Remember that coronary arteries also, feed the heart with blood, feed the brain as well. So when you have ischemia in those arteries, when those arteries are blocked, caused by bubbles in the blood, that is trouble, okay? Occlusion of blood vessels in the brain and spinal cord. You have damage to tissues in the brain and spinal cord, dizziness, paralysis of muscles, shortness of breath, and choking. Finally, what happens is the person becomes fatigued, unconscious, and then he dies. So let's look at the difference between nitrogen narcosis and decompression sickness. Like I said, both are caused by nitrogen, okay? Nitrogen is caused by breathing such a high concentration of nitrogen, okay, such that it almost acts like a mild anesthetic. When some people go for surgery, they give them anesthesia. Some have local, some have general. But anesthesia is something generally that makes you pass out, okay? You don't feel pain or anything, okay? So nitrogen starts acting as a mild anesthetic at such high concentrations. Remember, we said nitrogen is an inert gas. Okay, but when you switch to a high concentration of hydrogen, it starts to act in another way, like a mild anesthetic. Okay, so that nitrogen that causes nitrogen narcosis remains dissolved in that diver's blood, in its tissues. It doesn't form bubbles. But decompression sickness is caused by that nitrogen coming out of solution, no longer dissolved in the body. It comes out of solution and starts forming bubbles. So where do the bubbles come from? You're wondering, where exactly do these bubbles come from? Now, during every dive, the diver's body will absorb the nitrogen from his breathing gas. Okay, it absorbs nitrogen from there. As he ascends, the nitrogen expands according to Boyle's law. Remember Boyle's law, P1V1 is got to P2V2. Remember, normally that nitrogen will travel in the diver's bloodstream until it reaches his lungs, where he can now exhale. Okay, but if the diver stays underwater for too long, every diver has his no decompression limit. So he stays past his no decompression limit, or he ascends too quickly, his body would not be able to eliminate the nitrogen effectively. Okay, so that excess nitrogen will be trapped into his body, and form bubbles. Okay, so you said there's nitrogen narcosis, you know, it's like a condition where a person is intoxicated or drunken. Okay, he can't reason, he can't think right, he's in disarray. You know, these are all indications of nitrogen narcosis. Okay, so you said all of that. And divers will normally experience decompression ailment just a couple of hours to 1 day after a plunge, or during rising from an extremely profound or long plunge. So in contrast to nitrogen narcosis, the indications of decompression sickness, they are not observable during the diver's deeper part. Okay, so nitrogen narcosis, you can identify it with the depth that the diver goes to. Okay, the greater the depth, the deeper the narcosis. Okay, so and for whatever length of time he feels ordinary, you know, it's like you're in a state of euphoria. You just keep plunging and plunging and going deeper and deeper instead of being careful. Okay, that's how it is. It's like when you are driving, you know, and you first of all learn how to press on the accelerator for the first time. Okay, some people just like to speed and speed and speed, you know, which is not advisable. So for inexperienced divers, they do not know when their body starts to change or when they start to feel funny. So they just keep plunging, okay? So, and that is very dangerous. So the depth of the dive will also affect the type of narcosis which will be experienced. Now, decompression sickness is come about by nitrogen bubbles. Now, to treat this ailment, the diver we have to take out the nitrogen. So he rises by experiencing a repressure treatment. Sometimes put them in hyperbaric chamber. You put them in a hyperbaric chamber. So the more drawn out the air bubbles stay in the diver's body, the more harm they will cause. So decompression sickness is very perilous and time hazardous, which means you have to act fast because nitrogen bubbles in your body is a killer. Now, Scuba. Scuba is what we call self-contained underwater breathing apparatus. So it's just an acronym for Scuba. Self-contained underwater breathing apparatus. Scuba is its acronym. Is used by deep sea divers and underwater tunnel workers to prevent the ill effects of increased barometric pressure in deep sea or tunnels. So it can be easily carried. It's actually a cylinder, contains air cylinders. It has a valve system and a mask. So it facilitates breathing without high pressure. So that valve system, what it does is that it regulates the amount of air that is necessary during inspiration. So the air that enters the mask is regulated and the expired air is expelled out of the mask. Now, the disadvantage of Scuba is that it permits the diver to remain in the sea or tunnel only for a short period. That is for example, at a depth of greater than 150 feet. So only a few minutes is permitted. Now, again, there's such a thing called the Martini Effect. It's a term used in scuba diving to refer to the physical and mental impairment that it experiences. A martini is an alcoholic drink. Some people take martinis and there are different types, okay? It's not like gin, okay? So we say Martini Effect. It's like he has taken a martini and he starts having mental impairment, cannot think properly and all of that. Okay, so back to Henry's law. Now, Henry's law is important for scuba divers because nitrogen will dissolve in their blood when they breathe that compressed air at that depth. And when they are ascend to the surface, the pressure is released, nitrogen gas bubbles will be out of solution. That will cause painful symptoms and dangerous symptoms of decompression sickness. So imagine what it's like to have nitrogen bubbles in your joints, nitrogen bubbles in your arteries, nitrogen bubbles everywhere. And the longer you stay at that depth, the nitrogen bubbles just keep increasing and increasing and increasing. This is a link to a video to show you what exactly takes place. So you can watch that video, a very short 1-minute video I've put there for you. So this is your assignment. States the entity that is characterized with gas bubbles, explain the physiology behind its occurrence, and list the factors that increase bubble formation. Okay, now, if you have gone through these slides well and this lecture, as I have taken you through, and you, after the lecture, you take particular notes of everything I have said, you will understand and you would have been able to fulfill the objectives of the lecture. Okay, so this is a link that you copy, click on the link or copy into your browser, and then you'll be able to see much of everything I've been explaining also in detail. You'll be able to see Henry's law. You'll be able to see what actually takes place. You'll be able to see the factors that affect bubble formation. You'll be able to see how the gases work, much of everything I have said, and much of what is in your assignment, okay? If you're a good student, you take particular notes of everything I'm saying. All right, so let's go back to our objectives. Please take notes of everything I have said. So after the end of this, at the end of this lecture, I have explained how the effects of barometric pressure affect nitrogen concentration from the scratch, the effects of breathing high concentration of nitrogen. I have discussed the cause of decompression sickness. I've told you the difference between nitrogen narcosis and decompression syndrome. Okay, so this is, okay, so I have discussed that. Please, what I want you to do now, do your assignments. That assignment is 20 marks. I hope you have done the assignment of the other lecture as well, okay? And send to the email designated, just like I'll put on your WhatsApp group. Please go through the bibliography, it will help you. And always remember, be a good student. Thanks for paying attention and all the best. Be diligent, be focused, be positive, determined to bring light to your world, because you could actually be the next Nobel Prize winner. Okay. Thank you for paying attention. I will post the lecture on the group page or on the online platforms. As from now, you will see the first lecture and this on the online platforms, as well as your WhatsApp. Thank you for paying attention.